Okay, we're going to have an R session now in R Studio. We've learned about some techniques for fitting linear regression models, and now we're going to see how we do it in R. So you'll see I've got a session open in R Studio with some commands that I've already typed in, and I'm just going to go through these with you, and we'll see some of the features in R for fitting regression models. Okay, so here we are. We've got a script window over here, and we'll send commands down to the console. So first we'll do library mass, which has some data sets that we're going to access. And then we'll go library ISLR, which is our own library with data sets used in the book. Okay? And so first of all, we'll do simple linear regression. So one of the data sets is the Boston data, and it's got a bunch of variables. And if you say names of Boston, you see all the names of the variables. Well, they're kind of abbreviated names, and so if you want more detail, you can ask for help on Boston. So we do that by putting a question mark before Boston. Boston's a data frame, and in the right panel now, we see the help file for the Boston. So we see it's housing values in suburbs of Boston. It's got 506 rows and 14 columns. And now it tells you details about each of the variables. So CRIM, for example, is per capita crime rate by town. ZN is proportion of residential land zoned for lots over 25,000 square feet. And so on, if you go down the list. And these are all features about these regions in Boston. And they sort of summary features that describe the socio-economic conditions in those regions. LSTAT, lower status of the population, percentage. So it's a percentage of the population that in that region that's of lower status. And MEDV is median value of owner-occupied homes in $100,000. So you can do help on data frames. Okay, so the first thing we do is we fit a linear model. I beg your pardon. The first thing we do is plot some variables. So we'll plot MEDV and LSTAT, the two variables we just mentioned, and comma Boston, which tells the plot function to find those variables in the data frame Boston. And by using a twiddle between MEDV and LSTAT, you're actually telling it that really the response is MEDV. That's the median housing value. It's going to put that on the vertical axis. And so there's the plot on the right. And sure enough, as the lower status in the region percentage increases, the median housing value decreases. We'll fit a linear model now to those data. And you'll see the formula is the same as we used in the plot. And we call that fit1. And there it's fit. And then we'll print it out. And it gives us an intercept and a coefficient. And sure enough, the coefficient's negative. As you can see, there's a negative relationship. So printing out a linear model fit gives you a very brief summary. And for a more detailed summary, you can say summary of fit. And when we do that, we get a lot more. So we get residuals. Some of it's got cut off here. If you just look up, you'll see you get the call that created the fit. You get and then you get the coefficients, their standard errors, t-values, and p-values. And both of these are very significant. We're typically not interested too much in the intercept. It's the coefficient of LSTAT that we're interested here, and it's negative and very significantly so. And then there's some other summary material underneath, which we'll maybe touch on a bit later. Okay, so the nice thing, so notice in the formula here, we had the response on the left-hand side. Twiddle means is modeled as, and then LSTAT is the single predictor in this case. And then we give the name of the data frame where these variables can be found. So that's a standard format for fitting linear models. And there are other options too, but for the moment we won't need them. Now we can add that linear model fit to the plot. And there's a function called ABLine in R, which is able to pick up a linear model and just do that. And you'll see in the right-hand plot, it was augmented with the line that corresponds to the fit. Okay. Now, we've done various things with the fit. We've plotted it with this AB line. We've looked at it with summary and with print by just printing its name. You can see what other components on it. It actually has got quite a few components. These are largely to do with the details of fitting the model, and we won't trouble ourselves too much with them. But basically, you can see the coefficients on the fit, and that was picked up by the summary, and then a whole lot of other things that are used rather internally, so we won't really concern ourselves with them. Confint finds your confidence interval for the fit, and in this case it gives a confidence interval for the coefficients, and by default it gives the lower 25% and upper 97.5% bound, so this is a 95% confidence interval for each of those coefficients. The predict function is another one of these methods that we can use to query a linear model fit. In this case, we're going to predict with 3 new values for LSTAT, or 3 particular values, 5, 10, and 15. And we're going to not only ask for predictions, we're going to ask for a confidence interval. So those are additional arguments to predict. And when we do that, we get the fit at those 3 values, and then the lower confidence interval and the upper confidence band. And so you can give as many values as you like and get those lower and upper values. So that's simple linear regression. Let's move on to multiple linear regression. And now we fit a linear model fit 2, which is going to be a linear model with LSTAT and age. And we separate those with a plus in the right-hand side of the formula. And we can fit that and do a summary. Well, it's just much like we had before, except now we've got 2 coefficients, 2 standard plus the intercept, so 3 altogether, with their standard errors t-value and p-values. And age is also significant, quite strongly so, but not as significant as LSTAT. One of the things down below is the R squared, which we talked about as well. For the model, remember R squared, it's the higher the better. It's a percentage of variance explained. And it also gives you a summary, other summary of the model. The F statistic is the F statistic that we'd obtain if we dropped out both of the predictors in this model. Fit 3, we're going to fit a linear model with response med v, and it goes twiddle dot. And what that signifies is that we're supposed to use all the other variables in the Boston data frame except med v, which is the response, and all the others will be predictors. And sure enough, when we do a summary of that model, you see there's a lot of coefficients, and they each get their estimate, their standard error, their t-value, and their p-value. Most of them are significant, some are not. Age now is no longer significant. So age, when it was in the model just with LSTAT, was significant, but now it's in the model with all these other predictors, and it's no longer significant. What that means is there's basically a lot of other predictors that are very correlated with age, and in the presence of them, age is no longer required. Let's do a plot. You can plot linear models. I made a 2x2 layout because I know that there's 4 plots get produced when you do a plot. These are a little small here, but we can see what's going on. These give you various views of the linear model. The first one is the residuals against the fitted values. The vector of fitted values is just a single vector, so we can plot the residuals against that. And the reason we do that is we're looking for nonlinearities, and we kind of know there's a nonlinearity in this one. We saw that in the very first plot. And by the curve in the residuals here, we can see that the model's not quite capturing everything that's going on. There seems to be some nonlinearity. And there's other plots which are somewhat beyond the scope of what we're doing here today that give you aspects of the linear model fit. This one here is, this lower left one, is the square root of the absolute standardized residuals. One plots this to see perhaps if the variance is changing with the mean or the fit. In this case, it looks like there may be some relationship there, but that could be a result of the nonlinearity that we seem to have missed in the model. Update is a nice command. You fit a model, fit3, and you can update it. And in this case, we're going to update. The formula we give is twiddle dot minus age. Twiddle means nothing on the left means we're going to use the same response. Dot means whatever the model was in fit3, that's replaced in dot. And minus age means we want to remove age, and minus indus, we want to remove indus as well. So this will fit the model with those two variables removed, all the others in. And sure enough, if we do the fit, we see that those two variables are out, and now everything that's left in the model appears to be significant. Okay, moving on, nonlinearities. And interactions. The first thing we'll do is make a fit where we put an interaction between LSTAT and age, and that we do with a star, sort of like multiply, but in this formula language it means an interaction. And we've just got those two variables in the model, and so when we do a summary of the fit, we see that we get a main effect for LSTAT, a main effect for age, and then the interaction, which here is represented as a colon. So that star in the formula means that we're going to have main effects for each and the interaction, and the pure interaction is indicated by a colon. And while the main effect for age is not significant here, the interaction is somewhat significant. Next thing we do is we fit LSTAT, and we saw that there was a nonlinear looking scatter plot between MEDV and LSTAT. And so here we explicitly put in a quadratic term. And there's two things going on here. The one is the quadratic we indicate by LSTAT power 2, but power has a meaning in this formula language. And so if you wanted to mean actually just raise LSTAT to the power 2, we protect it with this identity function. So the formula language doesn't dig inside this identity function. So it literally puts in the square of LSTAT. And the other thing that's going on here is we've put two commands in one line, which you can do in R, but you have to separate them with a semicolon. So you can have as many commands in one line as you like, but separate them with semicolons. And so both of those commands got executed now. And sure enough, as no surprise, both coefficients are strongly significant, the linear and the quadratic. Okay, so now we're going to plot this. What I do now is attach Boston. We've seen this before. It means that the named variables in Boston are available in our data space. It just makes it easier for making nice looking plots. We go back to a single pane plot layout. So par mf row equals c 1 1. It means a 1 by 1 layout. And now we'll plot our two variables. There they are. We've seen that plot before. And now we'll include the quadratic fit. Now, we can't use AB line anymore because that only works when you've got a straight line fit. Now we need to somehow get the fitted values from our quadratic fit and include them in the plot. And so we do that with the points command. And the first argument is LSTAT itself. And the first argument. The second argument are the fitted values from fit 6. That was our quadratic fit. So the fitted values are, for each value of LSTAT, it's the fitted value from the model. So that's exactly what we want. And that'll be plotted as a series of points. And we tell it the color should be red. And the PCH, which is the plotting character, is to be 20. Let's see what it does for us first. Well, it puts the quadratic fit in the plot. Looks like the plotting character 20 is a little round ball. We'll have a little look in a moment and see a bit more about that. Before we do that, there's an easier way of fitting polynomials, and that's to use the poly function in R. And so here we're going to fit MEDV as a polynomial of degree 4 in LSTAT. And we'll add that to the plot with color blue. And you can see that the fourth degree polynomial is getting a little bit too wiggly. It's chasing out, it's starting to overfit the data a little bit, especially you can see in the right tail over here, it's maybe, you know, going after these rather isolated points here. Okay, so before we end, let's have a look at what plotting characters are available. So here's a simple way of seeing them all. Plot 1 to 20, 1 to 20, and plotting characters 1 to 20. And we can see the whole lot. And there you see them. And so you have available a whole bunch of plotting characters. There's actually more than these. And number 20 was sure enough this one over here. And Cx equals 2 means that we want to enlarge those plotting characters by 2. You know, we want to double the size. Qualitative predictors. So car seats is another one of the data sets. Okay. So the command fix is a way of throwing up an editor in R, so you can actually look at the data that you're about to use. So it'll throw up a data frame and allow you to use it. And so here's the car seats data frame thrown up on the screen, maybe a little bit small for you to use. Just wanted to show you that. I'll quit out of that, get back to our studio session. And so that's one way of seeing the data. There's the names of car seats. And so this was a study on children's car seats. Okay. You can also do a summary of a data frame, and for each variable, it tells you something about the values in the data frame for that variable. And you can see for quantitative variables, it gives you summaries like the mean, the median, and upper and lower quantiles. But for categorical or quantitative variables, it actually gives you a table of the distinct values. Okay, so shelf lock is a qualitative variable in this case. Okay, so we'll fit a model for the car seats data, and the first call is sales twiddle dot, means everything in the frame but sales, plus we're going to add in interactions between income and advertising and age and price. And we do that, and sure enough, there we get the model. And see, there's again a bunch of significant variables, and there are those two interactions we put in. And income and advertising appears to be strongly significant, but price and age is not. Shelf lock was a qualitative variable. If you look at contrasts function, it shows you how R will code that variable when it's put in a linear model. And in this case, it's a 3-level factor, and so it puts in 2 dummy variables, and the values are, if shelf lock is bad, 0 for both. If it's good, the first one is 1 and the second one is 0. If it's medium, see they named actually good and medium, 0 and 1. And so bad is not neither good nor medium, so that's 0 on both. So that you can actually find out how R codes quantitative variables. So the final thing we'll do here is see some examples of writing R functions. So let's write a little R function to fit a regression model and make a plot. So we start off by saying RegPlot is equal to function of xy, open curly brace, and then, so that open curly brace indicates that we're going to start giving the code in our function. And the x and y says our function is going to take arguments x and y. Okay, and so the first thing we do is we're going to fit a linear model between y and x. Then we're going to plot xy, And then we're going to AB line the fit with color equals red, and then close curly brace. That's the end of our function. Okay, so it's a very simple little function which we've written. And so now let's try it out. We'll attach car seats, and we'll do a RegPlot of price and sales. So it takes two arguments. We've given it price and sales. And you see the plot on the right. RegPlot silently went off and did that and produced the plot and put in the line. Okay. Well, let's make our function a little bit more useful. And you can see I'm defining it with essentially the same commands, but I've added a ... in the arguments. And this is a very useful construct in R when writing functions. ... means these are unnamed arguments, but you're allowed to add extra arguments, and they'll get passed on exactly as they supplied wherever they're used inside the function. And here I've passed them on to the plot function. And what that does is it allows us to add extra arguments to the plot function via our RegPlot. And so now when we make the call, we call RegPlot price and sales, and we give it XLab and YLab. So that tells it how to annotate the labels of the axes of the plot, and we add some color and other information. See, RegPlot just called the axes X and Y. Meanwhile, our variables were price and sales. So now when we make the plot, you see the plot points were colored in blue, and the axes were labeled. Okay, so that's a little introduction to some of the linear model software in R. The scope is really large, and there's many other things you can do. But, you know, as always with software, you've got to start at the beginning and get your hands dirty. And so we've done that a little bit here, and I encourage you to play with this yourself and explore the functions, use the help files, and see how far you can get.